We're back again. So we're going to solve out problem number 7. This one says a 1.0 liter buffer solution contains 0.100 moles of HC2H3O2 and 0.100 moles of NaC2H3O2. The value of Ka for HC2H3O2 is 1.8 times 10 to the negative fifth. Determine the pH after 0.010 moles of solid NaOH is added to the buffer solution. What are they doing to us? So what we need to do is recognize when to use stoichiometry and when we can use all our Ka stuff, but also when Henderson-Hasselbalch works. Maybe when it doesn't work, we'll explain that here at the end. But in this case, it still does. We'll see. But we're always going to start off kind of going through our scheme. We need to start off by writing a balanced net ionic equation. But notice that in this one, we have our an acid. And this acid, it's not a strong acid. It's a weak acid. And we got this thing. Oh, and we got, oh my goodness. Oh, we got a conjugate thing because take a look at this. This matches up with that. So yeah, we got a conjugate thing. And Na, that's one of our solubility rule things. So we're going to forget about Na and just go with C2H3O2. That must be minus because Na is usually plus. So we're going to use that. And then so we have this strong base that's being added to it. We'll get to that here in a second. Let's start off with our weak stuff. So we got this HC2H3O2. It's a solution. We're going to make it aqueous because it has this solution. Even though they tell us moles, it has liters. We'll get to that. But this acid, it's not just having water and reacting with water. Because they add this strong base to it, we're going to, and it's a strong base. So remember that when you see strong base, it dissociates into Na plus and OH minus. And we can just take it as the OH minus. So we have plus OH minus aqueous. Because we're dealing with a weak acid, it is still in equilibrium. And we have C2H3O2 minus aqueous. That's from my conjugate part over here. And also because this is an acid, it donates a proton, but it will also react with this OH minus to make water, H2O liquid. And I have no other spectator ions. I took care of the NAs, all that kind of stuff. So yeah, no spectator ions. This is my net ionic equation. Nice. So here's the thing. Because I have a weak acid reacting with a strong base, I have to do stoichiometry first. So if there's a weak acid or base reacting with a strong acid or base, I have to do stoichiometry. It's because there's neutralizing happening. So there's going to be parts in here where we need to determine things like if there's a limiting reactant and kind of what we mean by before values, after values. We'll get to that. But here we go. And so we need to do stoich, setting up a BCA table. And it's really nice because they told us moles. And when you're doing your BCA table, deal with it in moles. Use moles. And so this HC2H3O2, they told us we had 0.100 moles. And we had 0.100 moles of this C2H3O2. And that was over here. But for my NaOH, I have 0.010 moles. So when I have an acid and a base, they're going to react with each other. Yep, they're going to react and make some products. But I need to determine from here what my limiting reactant is, because that's going to determine my change and things like that. And so when I look at it, 1 mole of this should react with 1 mole of this to produce 1 mole of each one of these. But if I look at what I have 0.100 moles of this. If I kind of do that multiplier thing, take the number of moles, divide by the coefficient, 0.100 divided by 1, and 0.010 divided by 1, I end up with a smaller multiplier over on this side than I do on this side. That means that this one, or the OH, is my limiting. So when I do the reaction, all my OH is going to disappear, and it's minus X, because there's a coefficient of 1. And this one's going to be, also minus X. I'll get 0.100 minus X. And over here, my products are going to be plus X, and water, and we don't care about water. And so we don't have to worry about it because that's not going to affect our pH and things like that. And so now I have 0.100 plus X. But the nice thing about this is I already know what my value for X is, because 0.010 minus X is 0. That means that X has to equal 0.010 moles. So this, if I have 0.100 minus what I actually knew for X, I get 0.090 moles. And here I would end up with 0.110 moles. That's cool. So now that I have this information, I still haven't answered my question. Determine the pH after this is added. Okay, so I added that and figured out concentrations. But to figure out pH, well, I need either H plus or OH minus, but I don't have it here. So there's a couple of routes that we can do, but there is something that we need to recognize also. We have an acid and we have its conjugate. So here's my acid and here's the conjugate base. Okay? It's not a strong base, it's my conjugate base. So these are related. But if I have an acid and a weak acid and its conjugate base, that means I have a buffer. And that's really nice, because if I have a buffer, I do have two choices. And one is kind of long. If I choose, after doing this stoichiometry, I can go through and do the ice table. But because I have a buffer, I can determine the pH from the Henderson-Hasselbalch equation, because I know the concentration of my acid and the conjugate base. Oh man, so let's do this. So, because I have a buffer, I'm using the Henderson-Hasselbalch equation. pH equals pKa plus log concentration of A minus over the concentration of HA. So my acid and my conjugate base. Here's my base, here's my acid. So this isn't talking about the strong base. This is talking about conjugates. So my weak acid and my conjugate base. But I need the pKa, but I have Ka. Oh man, so pKa is equal to negative log of Ka. So I need to do that first. Negative log of 1.8 times 10 to the negative fifth. My pKa will come out to be 4.75 or 4.745. There we go. Then, now that I have that, I can put this into my Henderson-Hasselbalch. pH equals 4.745 plus the log of, now that I know these concentrations at that I have after the stoichiometry, my acid is 0.090. That has to be on the bottom. So something else that we got to take into consideration here is that in this equation, these values are concentrations. These are moles. We need molarity. So before we actually put it into here, so plus log, we need to figure out the molarity. This is really nice though, because with molarity, remember it's moles over liters, and it's 0.090 moles divided by this 1.0 liters, and this will be divided by 1.0 liters as well, because that is the volume of our solution. So this one's pretty easy. It's just 0.090 divided by 1, we get 0.090 molar. That is my acid, so it has to go on the bottom. And then my base, it's my conjugate base, and its molarity is 0.110 divided by 1.0, you get 0.110 molar. And that's my base. It's my conjugate base. Sorry, conjugate base. Not my strong base, not that. And now I do the math, and when I do that, my pH will come out to be 4.832. When I look at sig figs, I got 3 sig figs, 3 sig figs. Oh, I only got 2 sig figs here, so I should probably only have 2 sig figs for my pH. Remember, pHs, the sig figs are counted after the decimal, which is kind of funky. But 4.83, that's the pH. And I could do that and use Henderson-Hasselbalch here because I was dealing with a buffer. Otherwise, I would have to do something very complex to figure out the concentration of OH minus or H plus. I'd have to actually figure out which way this would shift. I'd have to figure out all this other stuff, which is just, yeah, it should shift this way or back this way. It's messy though. Don't do it. And Henderson-Hasselbalch, if you have a buffer, that's the way to go. All right, but we'll see you guys here and for the last problem. And part of it's easy. The other part's fun. All right,